Okay, thanks for the introduction. So I guess there are a lot of words in the title, and hopefully they'll make sense by the end of the talk, but just as an overview, this talk is about interactive proofs in the presence of quantum entanglement and what they can do. So, and this is joint work with Toma Vidic, who is in the audience, and I guess we're both at Caltech. So let me start by just reviewing some classical background about interactive proofs. Probably will be familiar to you. But so the most basic model of interactive proofs is you have a prover who's all-powerful, who gets to interact with a verifier that's computationally bounded, and the verifier wants to learn the answer to some problem without being able to do it himself. So in this model of IP, where there's just one prover and one verifier, it's known that this is equal to p-space, and it's due to Shamir. So the prover only has polynomial power, but it can solve p-space problems with access to this. I mean, sorry, the verifier has polynomial power, but it can solve p-space problems with access to this prover. Okay, so what if you have, you could consider extensions to this model, and one very interesting extension is multi-prover interactive proofs. So if you have two provers, and you sort of physically separate them, so you put them in separate rooms so they cannot talk to each other, and then you interrogate them separately, then you might imagine that this would be a more powerful class because you can limit their ability to cheat you. And indeed, this is true. So it was shown that this class MIP of multi-prover interactive proofs is equal to nexp, so non-deterministic exponential time. Okay, so that's great. What about in the quantum world? What if we add quantum to these things? So you could imagine adding quantum in many ways. So first, you could take this single prover model, and you could imagine making the prover and verifier both quantum and adding quantum messages. And it turns out this doesn't really change the power of the class, so it's still equal to p-space. What about the multi-prover model? So here there are actually many choices you could make. So you could add quantumness to the verifier, so you could make it a quantum polynomial machine. You could add quantumness to the messages, or you could add quantumness to the provers. And this is actually sort of interesting. So in the single prover case, like adding quantumness to the prover was actually sort of meaningless because the prover was assumed to be all-powerful. But here, in the multi-prover case, something very interesting can happen, which is that you can have two computationally all-powerful provers, but they're forbidden from communicating. And now quantum mechanics allows you to do something special, which is you can have an entangled quantum state. And using entanglement, you can do things that you could not do with just classical shared correlations or shared randomness, even though you can't communicate. So based on this, we define a complexity class MIP star, which is basically the same as MIP, so classical polytime verifier, classical messages, but the provers are allowed to share an entangled state that they agree upon in advance. Okay, so what's the power of this class MIP star? So the first thing to note is that it could actually potentially be weaker than MIP. Why is that? Because the provers in MIP star have more power, so they could cheat you. It's more possible for them to cheat you. So proof systems that are sound against MIP provers may no longer be sound against entangled provers. And indeed, we have examples of this. So this work by Cleve, Hoyer, Toner, and Watrous, they showed that this class of XOR proof systems, which is classically sound, and these things can solve NX problems. Like in the quantum case, when you add entanglement, the power of this class is contained in X. So, so entanglement destroys the soundness of some protocols. However, you can show that other protocols for NX are actually sound against entanglement. So it turns out this class is indeed at least as powerful as MIP. Another weird thing about it is that there's no upper bound, like not even a trivial upper bound. So in the case of MIP, like the inclusion MIP in NX is easy to see because you can imagine just writing down a complete transcript of every possible answer that the provers would give to every question they might receive. And this is an exponentially large object, and you could just guess the transcript, and that's in NX. But when you have entangled provers, a priori, you're not placing any restriction on how big of an entangled quantum state they're allowed to share. And like, we have no way of bounding the size of the entanglement they need to realize some distribution. So especially because the psi could be arbitrarily big, there's no upper bound on this class. So the natural question that arises is, what's the best lower bound that we can prove, and in particular, can we prove lower bounds that are stronger than the classical ones? So what's a lower bound that you could conjecture? So let me just restate the MIP equals NX result, but it's not quite a restating, but this is a more refined result that you obtain when you scale down the provers and the verifier. So when you scale them down, you get this result that NP is equal to MIP with log size messages, and the second two parameters written here are the completeness and soundness. So the completeness is like the probability that you accept a correct proof, and the soundness is the maximum probability of accepting a wrong proof, in the case where the answer is really no. So there's this constant gap between completeness and soundness. So you have the constant probability of detecting a mistake. So this thing is essentially the PCP theorem. You may have seen it in a different guise, but it's equivalent to the usual formulation in terms of proof checking. So we could imagine that maybe for this MIP with shared entanglement, there's a sort of quantum PCP result that might be true. And what would that be? That would be if you just take this thing and you stick quantum on both sides. So the quantum version of MIP is MIP star, and the quantum version of NP is this class QMA. It's just like NP, except the verifier is quantum, and the witness that it might receive is a quantum state. Okay, so this is the game's quantum PCP conjecture. I think it was first conjectured by Fitzsimmons and Vidic in 2014. So hopefully I've convinced you this is sort of a natural thing to conjecture that might be true. So why would we care about proving this? So there are a couple interesting consequences, I think, if you show this is true. So the first is that if you assume that QMA is not equal to NP, which we indeed think is true, then you'd be showing that these entangled provers are strictly more powerful than provers without shared entanglement. And that's interesting. The next thing is that if you designed a protocol that achieved this, that protocol would have the property of certifying that the provers share a large amount of entanglement. And why is this? It's because you can show that if the provers share a small amount of entanglement, then MIP star is actually still equal to NX. So in order to achieve like power beyond NX, or I guess in the scale down setting beyond NP, you need to share a large amount of entanglement, like an amount of entanglement that grows with the instance size. And that's interesting just independently, because often we want to we might build a quantum device and want to figure out a way of testing that entanglement is present. And entanglement is a useful resource for many tasks. A further application is the class QMA contains BQP, quantum polynomial time. So if you can solve QMA problems, you can also solve BQP problems, and maybe this could lead to efficient delegated computation schemes. And then finally, so in the classical world, this multi-prover interactive proofs view of PCPs was very fruitful, and it also eventually led to a great deal of hardness of approximation results. And we could imagine that although these connections are not so clear in the quantum case, there still might be some way of obtaining hardness of approximation for quantum problems, like the local Hamiltonian problem, like QMA problems, using techniques that we developed for this. Okay, so these are, I think, a few reasons to maybe want to prove this conjecture. So there's been a fair amount of previous work on this, so I'm going to skip over some of the results and just tell you the two most recent things. So there's, it was shown by G in 2015 that if you allow the completeness soundness gap of your protocol to be small, so if you allow it to be inverse polynomial in the instance size, then you can solve QMA. So classically, if you've heard of the clause variable game for CSPs, this is sort of a quantum analog of that. And then we had a paper in Stock in 2017 that showed that if you have a large completeness soundness gap, but you blow up the message size to be polynomial, then again you can solve QMA. And this is, maybe you could think of it as like analogous to the toy PCP or exponential PCP based on the linearity test. So you can see in these previous results there was this trade-off between the message size, so we ideally want log n bits to be communicated, and the completeness soundness gap, which we want to be a constant, but here is smaller than constant. So, okay, so Now I'll get to our main result. So our result is essentially that we were able to obtain both of these things, and so we can prove a version of this quantum games PCP conjecture. So our main theorem is that there is a 7-prover proof protocol with entangled provers that has log-size messages and some constant completeness soundness gap. You can adjust it by hardness amplification for QMA with a little caveat. So it's really under randomized reductions. So what does that mean? That means we give a protocol for a particular problem, which I'm calling here the gapped non-local Hamiltonian problem, and that problem is QMA complete under randomized reductions. Okay, so that's the main result, and for the rest of the talk, I'm going to tell you sort of roughly what the protocol looks like and what the technical tools are that we use to analyze its soundness. So, okay, so how does a protocol for this problem look? Well, recall that QMA was like the quantum version of NP. So there's some witness, and you have to check that it satisfies some conditions. So the way we're going to design our protocol is we're going to ask that the ideal provers who are behaving honestly share a copy of this quantum witness distributed in some way. I'm not going to tell you how, but there's some encoding that lets them share this witness state. And then we're going to do one of two things. So some fraction of the time, we're going to do what's called an energy test, and it's just going to verify that the witness that they hold is actually a solution to the QMA problem that we're considering. And these QMA problems all involve measuring the energy of a quantum state, so that's why the word energy is used. But then we have to actually certify that when they claim that they're measuring this shared witness, that they're actually doing what we asked them to do. And so for some other fraction of the time, we have to run some sort of encoding test that certifies that they indeed share a valid quantum state that's encoded in the way we want it to be, and that they're measuring it correctly when we ask them to measure it. So the encoding test is, I think, where we spend most of the work in analyzing this protocol, so I'm going to focus on that and tell you about the tools that are used there. So in this encoding test, I somehow need to check that if the 7 provers pass, they have to hold an entangled state consisting of many qubits. So you could just start with the most basic question in this area, which is, how can I design a test that certifies that the provers have just one qubit? And this is actually a classic idea that goes back way back into the physics literature. So in particular to the foundations of quantum mechanics. So maybe you would have heard this story that Einstein was not very happy with quantum mechanics. He discovered that these entangled states can enable some very weird, spooky sort of behavior. And later on, inspired by some of the thought experiments Einstein had, Bell came up with an experiment that you can perform where the predictions you see from entanglement are separated from the predictions you could obtain from any classical system. So there's a simplified version of Bell's experiment, which is called the CHSH game. And this game is very simple. So it's like an interactive proof. It's an MIP star protocol, you could say, for where there's 2 provers and 1 verifier, and they just exchange single-bit messages. And I've written here what the actual predicate of the verifier test is, but it's not so important what it is. The important property of this thing is that, first of all, classical strategies can only win with some probability far from 1. So with probability 3/4, a classical strategy can win this protocol. Whereas a strategy sharing entanglement can succeed with higher probability. So for CHSH, it's closer to 85%. And secondly, you can use this to test that, if you pass this CHSH test with high probability, you can certify that there's indeed a qubit in a particular entangled state. So this is this thing called, this property is called self-testing in the quantum information literature. And sort of the statement is something like, if you succeed with probability that's epsilon close to the optimal probability, then the state that the provers share has to be some function of epsilon close to this ideal state. Okay, good. So this guy is Cyrilson, so he's the one who showed that the optimal quantum probability is this number 85%, and his ideas, I guess, are also behind the proof of this robustness result. So the intuition behind this thing is I think, sort of valuable, and maybe you saw it earlier in previous talks on verifying quantum computing. So the way you show the statement is you say that in order to succeed with close to the optimal probability, the provers have to use measurements that anti-commute with each other, and that's only possible to achieve on qubits. And then once you've obtained this characterization of the measurements, you can also obtain a full characterization of the state. Okay, so what we do is essentially a sort of a larger version of this, a larger scale version of the CHSH test. And so the main lemma that I think is behind the analysis of protocol is this quantum low degree test. So that's where low degree test comes from the title, which is that there's a test for n copies of that state I showed you on the previous slide, where the communication is only log n bits, and there's a constant completeness soundness gap. And this is a 2-prover test, but it turns out that you can lift it to a 7-prover test for those encoded states that I showed you earlier. So if you can test for these so-called EPR pairs, then you can test for these encoded states. And why is it called a low-degree test? Well, it's actually built on the classical low-degree test that was an essential ingredient in the PCP theorem. So essentially what it does is a quantum state is a thing that you can measure in one of several different bases. So here we're considering 2 bases called the X and Z bases. And when you measure it, you get a classical string. That's your outcome. So what we do is either we pick one basis or the other, send it to both provers, and run this classical low-degree test, or we perform a lifted version of the CHSH test where we send basis X to one prover and Z to another prover and check that their measurement outcomes agree in the same way that CHSH measurement outcomes should agree. So what this achieves is sort of, the first part is checking that, like, it's sort of verifying that you have many classical bits. You could sort of think of it that way roughly. And the second part is checking that these classical bits are obtained from 2 quantum bases that are related in the correct way. And so when you put these together, you can check that you have n qubits and you're measuring them accurately. So once you have this, it turns out the energy test is sort of, you can do it by combining this test that I showed you for the encoded state with some classical PCP technology. So I'll just say at a very high level what it is. So the energy test, remember, was that once you had this QMA witness, you want to check that it satisfies the property that's being verified in your QMA problem, which is that the expectation value of some property, the energy, should be low. So essentially what we do is we just ask the provers to measure the energy and compute a classical PCP proof of the claimed value of the energy. And then it turns out that if you use the right PCP and you do some tricks, that the bits in this proof correspond to the measurements that were done in the encoding test on the previous slide. So if you succeed in the encoding test, you must be measuring those bits accurately, and therefore you're obtaining, you know, an honest PCP proof. And then by the soundness of these classical proof systems, you can check that the energy was measured correctly. Okay, so just to wrap up, let me just summarize what I did. So I said there was this protocol for this QMA complete problem that consisted of 2 parts. One was this quantum low-degree test, which checks that the provers share a highly entangled quantum state in the correct format. And then the second was this energy test that checks the particular QMA problem that you care about. So now I'll wrap up by giving you some open questions in this area. So the first is going back to this thing about better lower bounds for MIP star, which was the motivation for this project. So I conjectured, or I quoted this conjecture of QMA being contained in MIP star just as an analogy with the classical PCP theorem, but I mentioned that there's no upper bound for MIP star. So there's no reason necessarily that you have to stop at QMA. You could imagine, you know, asking for much better lower bounds. And recently we had this very interesting result by Fitzsimmons, G, Vidic, and Yuan, who showed that if you let the completeness soundness gap shrink, the power of this class becomes stronger. So you can get, in fact, like non-deterministic doubly exponential time or triply exponential time if you let the completeness soundness gap get, you know, exponentially small. And so it'd be very interesting to improve these results. And there are some deep connections here. So there's a problem in operator algebras called the Kahn's embedding conjecture, which turns out to be equivalent to a certain question about, like, whether two-prover MIP star protocols can solve undecidable problems. So potentially you could resolve this question if you showed better lower bounds. So I think that's one very interesting direction. Another direction is whether you could convert these these multi-prover protocols into cryptographic protocols with a single prover. So I guess we've heard about how this can be done in the classical world with non-signaling MIPs. Like they can often be compiled to single prover argument systems, and I don't think we really have such an analog in the quantum world yet, but I think that'd be very interesting. And also maybe like we could use ideas. So we've heard from Urmila's talks on the past few days about recent breakthroughs in the single prover setting, and maybe some of those ideas could be combined with this work. And then as I mentioned, there's like this constraint satisfaction or hardness of approximation version of quantum PCP that seems somewhat connected in spirit, but not directly, but maybe we could use these ideas there. And then finally, the protocols I showed you are experimentally often not very realistic because they involve the provers performing some complicated multi-qubit measurements. Maybe there are more experimentally realistic protocols that we could use in the near term. So thanks for listening.
Why 7?
It's because we use the 7-qubit CSS code.
Oh, it wouldn't work with a 5-qubit.
We don't know how to make it work, but there's no fundamental barrier that I can see. Yeah.
Actually, I have a question, but that might be from my ignorance. You said there's a small entanglement case is equal to an X.
Yeah.
Is there an NP version of that?
I'm not sure.
If you get log n bits instead of,
I
polylog n?
I think if you have log n bits of entanglement, that might be the case, because you could represent the. Well, I'll have to think about it, but I feel like it should be true.
I mean, it should be
But yeah, I should check the